All right, guys, this is Mrs. Lyons, and our next unit is called Thermochemistry. And from the word thermo, hopefully you recognize that thermo relates to heat. So this unit is going to be dealing with the heat that goes along, either that goes into a reaction or that is a product of a reaction. Okay, so in order to do this, we have to define a couple of things. And I will tell you right now, this unit is fairly heavy on vocab. So this might be a good one, maybe to make some note cards, flip through when you got a few extra minutes, just to make sure you've got your terminology down. Okay, so we're going to talk about the system and the surroundings. Okay, so the system is defined as the part of the substance. It's what we're studying. Okay, so it's whatever part of the universe we're studying. Okay, um, if we're doing a reaction, it would be what we're doing the reaction in. Okay, and then we have the surroundings, and the surroundings are basically everything else. Okay, so the surroundings is everything outside of our system. So for example, if you were to be studying a reaction, the reaction was taking place inside in a jar. Okay, the jar and what was in it would be our system, and everything outside of the jar would be the surroundings. Now it's important to know this because we're going to talk about um, we're going to talk about heat, and we're going to talk about the way heat moves. Okay, um, and how that heat moves depends on our system matters. Okay, because we're going to be talking about, does heat go into the system or does it come out of the system? Okay, so energy that moves from one object to another due to a temperature difference is what we call heat. Okay, and um, for chemistry, the transfer of energy happens through collisions. Okay, so we've got particles, and when they run into each other, energy is transferred from one substance to the other. Okay, something important to note, very important to remember: heat always flows from a warmer object to a cooler object. Okay, so when you open the door on a cold winter day, okay, the heat from inside the house is going to go out the door. The cold isn't really coming in, although sometimes it feels like it, but the heat from inside is exiting the house, going outside. All right, we have some terminology, okay, for this unit. We have two terms that are basically the opposite of each other. So one of the goals we need to have for this, getting into this, is remembering which of these terms is which. Okay, if heat energy is released, okay, in other words, it's leaving the system going into the surroundings, this is called an exothermic reaction. Okay, heat is exiting. The way I think about it is exit. So heat is exiting the system. All right. If heat energy is absorbed from the surroundings, okay, we say we have an endothermic reaction. RXN stands for reaction. Okay, so if you look at this picture real quick, this picture shows us an example. We have a Bunsen burner, we have we have an Erlenmeyer flask, And inside the Erlenmeyer flask, we have a reaction going on. Okay, so the flame from the Bunsen burner is putting heat into our system. Okay, now if we break that down a little bit more, okay, this is just like a really narrowed in view of this. We have air particles between the bottom of the beaker and the heat, okay? And then we have the glass, and then we have our reaction chemicals, okay? What happens as we heat the air, the particles move faster, which causes more collisions with the glass, okay? Those collisions are where heat is transferred. So heat is transferred from the particles to the glass and then to the liquid chemicals inside the flask. Okay? All right. So we are just going to practice our system and surroundings on this sheet. Okay? So we want to identify what is the system, what is the surroundings, and is this an endothermic or exothermic reaction? Okay? So hand warmers. You know how hand warmers work? You snap them and then you put them in your gloves, or you hold them in your hands, or I've seen people put them in their shoes. Okay, the system is the hand warmer. The surroundings is your hand and everything else. Okay, if you think about what's happening, heat is leaving the hand warmer and going into your hand. Okay, so your hand's going to get warm. So this is going to be an exothermic process. All right, ice cubes melting. All right, our system is our ice cube. The surroundings is the room. Okay, now sometimes I've got to think about these. I've got to really kind of focus on what is going on. So I have my ice cubes. And if you think about it, ice, water freezes at 32 degrees Fahrenheit or 0 degrees Celsius. Okay, so that ice is essentially at 0 degrees Celsius. The air in the room around the ice is warmer than that, 25 degrees Celsius probably. So what happens is the heat from the room goes into the ice cubes, causing the ice cubes to melt. Okay, so this is an heat is going in, endothermic reaction or process. An ice pack on an injury, similar to the hand warmer. The system is the ice pack. The surroundings is your body part where the injury is and everything else. Okay, the room, the air in the room, etc. All right, so an ice pack is cold. Now, when I think about an ice pack, you put an ice pack on to cool your leg down, right? So you would think that the cold is being transferred. In reality, cold can't transfer, heat transfers. So the heat from your leg, if it's your knee that got injured, the heat from your injury is going to go into the ice pack. And eventually the ice pack is going to warm up to room temperature. Okay, so the heat is going into, or endothermic, into the heat from your leg is going into that ice pack. And then finally, a bonfire. Okay, the system is the wood and the fire. The surroundings is the air around it, everything else essentially. All right, if you think about what's happening here, we have a bonfire, it's hot. Okay, and this one makes sense. The energy or the heat is leaving the fire. It's actually warming up the air around it. So it's leaving, so that's an exothermic reaction. Okay, so let's talk a little bit more about this whole idea of endothermic, exothermic. All right. So I guess first thing we're going to do is I'm going to show you a picture of these things called enthalpy diagrams. All right. An enthalpy diagram is just a picture that helps us identify what's going on in a chemical reaction. Okay. It shows us the change in enthalpy or the change in heat. Okay. A couple of things I want you to notice. Okay. So the x-axis is the reaction progress. We could also say that this is time. Okay. So at time 0, so if we're putting two things together, okay, when we combine them, that's time 0. Okay. Now, this line represents the energy of the reaction. Okay. So notice these two graphs are different. One is endothermic and one is exothermic. So this one is our exothermic. This one is our endothermic. Okay, but there are some things in common. So at time 0, we always start with the reactant. So we're going to just draw, and there's no necessary rhyme or reason to the height of things or the length of things. It's kind of a general idea. Okay, so we always start with our reactants, and then we end with our products. Okay, in an exothermic reaction, the products are at lower energy than the reactants. Okay, so if I were doing a reaction, my reactants would be here, my products would be here. Okay, so this is my potential energy. Reactants are at higher energy than products. Okay, in an endothermic reaction, notice my reactants are at lower energy than the products. All right, so the reactants okay. So that just means the reactants are lower on the y-axis than the products. Okay, we have to define two terms. Okay, the first one, the definition is down here. The minimum amount of energy that's required to start a reaction is called the activation energy. Now, if you think about activation energy, think about when we light a Bunsen burner. Okay, I have a Bunsen burner. Okay, I turn on the gas. Okay, and methane gas comes out. That's my fuel. There's oxygen in the air, which is required to burn, for something to burn. So why doesn't the fire light right away? Well, we have this activation energy. So when we use a striker or the little clicker that I have, that gives it just a spark of energy, just enough energy to make the Bunsen burner light and the reaction to go. Okay, so activation energy is, okay, and this is where it shows up on this graph. It's from the reactants energy to the peak of the graph. Okay, so in an exothermic reaction, and notice I've got these kind of dotted lines here that help me see, okay, extend that line across from the reactants up to the peak, and we abbreviate this E sub A, activation energy. Okay, so activation energy goes from the reactants to the peak of the graph. Now look at what we have in our endothermic. From the reactants all the way to the top is our activation energy. Okay. And then the other thing that we need to identify on this graph is delta H, which is the change in enthalpy or heat. Okay, and on the graph, the way that we identify it, it's the distance from the reactants to the products. So in my exothermic reaction, my delta H is from my reactants to my products. Now I want you to notice something. I drew that arrow and I drew it going down. What we're going to find out is energy, the amount of energy in an exothermic reaction is negative. So that kind of makes sense. That arrow is going down to a lower point. All right. On my endothermic graph, okay, the difference is from the reactants to the products. Again, if I start drawing at the reactants and I go to the products, I'm going up. Delta H is going to be positive for an endothermic reaction. Okay, so this is my delta H. All right, now let's talk about, we keep saying these two words, endothermic, exothermic. Let's talk about what endothermic and exothermic mean. All right. So an exothermic reaction, okay? Now these are this list here, these are a bunch of facts that you're going to need to remember, okay? So this isn't a real math heavy unit, but we do have some vocab that is going to be really important. Okay, so an exothermic reaction is a reaction where energy is released as a product of the reaction. So notice here I have my flask, the arrows are going out. That means heat is exiting the system. That tells us it's an exothermic reaction. Okay, if we calculate delta H of the reaction is going to be a negative value. Okay. The reaction container. So if I had a beaker or a flask and I was doing a reaction, the container would feel warm or even sometimes hot to the touch. All right. Heat is leaving the system and going into the surroundings. I'm going to show you in just a minute. We're going to use this heat and we're going to put it into our chemical equation. When we have an exothermic reaction, the energy is located on the right side or the product side of our equation. Okay, so let me show you some examples of this. Okay, there's three ways that we might see an exothermic reaction represented. Okay, we could see, and I'm just going to write these equations. So this is a chemical reaction where we're reacting iron plus oxygen, and we are going to produce iron oxide plus heat. Okay, so just the fact that that heat is on the right side of the equation tells us that that's exothermic. Okay, we also might see this written. This is the same reaction, it's just a different way of representing the heat. We might actually see it as a number, okay, so a specific amount of heat in kilojoules, okay? That amount, again, is going to be on the product side of my reaction. That tells me it's exothermic. And then finally, we might see this written that's not necessarily an immediate part of the reaction, but we might see it expressed as separate from the reaction. Delta H is equal to minus 1625 kilojoules. Okay, so we might also see it expressed just as a statement in addition to our chemical equation. The fact that this is a negative value tells us that it's exothermic. Okay, all right. So if we look at our graph, okay, this is an exothermic graph because the reactants are at a higher energy than the products. So we want to label this. Okay, I'm going to label reactants, or R would be fine. And then over here, this bottom is my products. Again, P would be fine. Okay, now this distance here from the reactants to the peak, that is our activation energy. That's the amount of energy it takes to get the reaction to start. All right. And then our delta H is the difference between the reactants and the products. And since from the reactants to the products, it's going down, delta H is going to be a negative value. All right. So now we're going to talk about the exact opposite. We're going to talk about endothermic reactions. Okay. So an endothermic reaction, okay, is when heat energy is going into the system from the surroundings. Okay, energy is being absorbed. All right, the delta H of the reaction is a positive number. The reaction container in an endothermic reaction will feel cool to the touch. All right. In an endothermic reaction, heat is entering the system from the surroundings. And the energy, or kilojoules, is on the left side, or the reactant side of the equation. All right. So now let's look at some examples. Okay, these are called thermochemical equations. It's just a way of writing a chemical equation incorporating the amount of heat that's gained or lost. All right, so we might see this as, for example, calcium carbonate plus heat produces calcium oxide plus CO2 carbon dioxide. Okay, the fact that my heat is on the reactant side tells me that this is an endothermic reaction. All right, we might also see this as a specific number. So calcium carbonate plus 176 kilojoules produces calcium oxide plus carbon dioxide. All right, by giving it a value, this tells us exactly how much heat, in this case, is absorbed because it's endothermic. And then finally, we might see it, just like we did with the exothermic, we might see it expressed not as part of the reaction, but as a statement that goes along with the reaction. Okay, so we might see it as a separate thing. Delta H is positive 176 kilojoules. And it's the fact that this is a positive number that makes it endothermic. Okay. So over here, this negative makes this an exothermic reaction. Okay. All right. And now, finally, our reaction, our enthalpy diagram. Okay, we're always going to start with the reactants on the left, the products on the right. All right, the distance from the reactant, so this arrow is a little misleading, but the distance from the reactants to the peak of the graph, okay, so it's a big amount on this one, that is going to be our activation energy. And the distance from the reactants, and I'm just going to make this like it's a graph paper. I'm just going to draw little lines so that I know where my lines are, okay? Delta H, the change in enthalpy, is the difference from the reactants to the products, okay? And since delta H is going up, okay, that means it's a positive number. Okay, so delta H is positive. Okay, something that I want you to note, and I didn't really stress this, when we put a number into our chemical equation, okay, the number is always listed as a plus. Okay, whether it's endothermic or exothermic, we count it as plus that amount. It's whether it's on the reactant side or the product side that tells us if it's exothermic or endothermic. And then if we write it outside of the equation, a negative delta H is exothermic, a positive delta H is endothermic. All right, so that is a quick introduction to thermochemistry. Again, I can't stress enough, this is a lot of, this test is different than our last couple of math tests. This test is kind of facts, knowing what is endothermic, what is exothermic, what are the differences. All right, I hope this video was good and helped you get an idea of what we're going to be talking about in this unit. I will see you in class. Take care of yourselves.